Most of us perceive time as a steady, reliable metronome ticking away in the background of the universe. In reality, time behaves as a malleable dimension, stretching and warping based on how you move through space. For centuries, classical physics relied on Isaac Newton's assumption that the universe had one master clock. Space was the flexible stage where things happened, while time was the absolute, unbending measure of when they occurred. That assumption held until 1905, when Albert Einstein published his theory of special relativity. This framework proved that space and time are permanently linked into a single fabric, and that the rate at which time passes depends on the motion of the person measuring it. To understand the nature of the universe, we have to let go of our everyday intuition and accept that reality operates by a counterintuitive set of rules. Einstein's realization didn't come from a laboratory experiment. It emerged from a thought exercise about the nature of light. He recognized that the entire structure of the universe relies on a single, unbreakable physical law. That law is the speed of light, the absolute cosmic speed limit of approximately 670 million miles per hour. This speed remains exactly the same for every single observer, regardless of how fast that observer is traveling. If you chase a beam of light in a rocket ship moving at 99% of light speed, you won't see that beam creeping slowly ahead of you. You will still measure it zooming away at exactly 670 million miles per hour. Because speed is simply distance divided by time, a fixed speed limit creates a physical contradiction. Since the speed of light can never change, the distance traveled or the time elapsed must be the variables that yield when objects move at high velocities. To see how this works, we use a theoretical tool called a light clock. Inside a stationary spaceship, a single particle of light, or a photon, bounces straight up and down between two parallel mirrors. Each time the photon strikes a mirror, the clock registers one tick of time passing. For an observer standing completely still inside that ship, the photon traces a vertical, predictable path. As long as you and the clock share the same stationary frame of reference, the distance the light travels is constant, and time behaves exactly as we expect. The physics change the moment we launch that spaceship. Imagine standing on Earth, completely stationary, watching the ship fly past at an immense speed. From your vantage point on Earth, the photon's path is different. Because the ship is moving forward through space, the light particle is dragged along horizontally, tracing a diagonal zigzag trajectory. This creates a geometric problem. A diagonal line is always longer than a straight vertical line. To your eyes, the light particle now has a greater physical distance to travel between each tick of the clock. In any other scenario, an object covering a longer distance in the same amount of time would have to increase its speed. But the speed of light is a hard constant. That photon physically cannot speed up to cover the extra diagonal distance. Since speed is distance divided by time, and the distance has increased while the speed has stayed the same, the time component itself must increase to balance the equation. The duration of the tick is the only variable left that can stretch. This is time dilation, the physical slowing of time for objects in motion relative to an observer. The faster an object moves through space, the slower it moves through time. Time functions as a physical, flexible dimension that bends to preserve the speed of light. This isn't just a quirk of light pulses. Every atomic interaction and every metabolic process in your cells relies on the same electromagnetic forces that govern that bouncing photon. If the atomic clocks in your body tick slower, your biological aging slows with them. This is the basis of the twin paradox. If one twin stays on Earth while the other travels the stars at near light speed, the traveling twin will return physically younger than their sibling. We have real-world proof of this. When astronaut Scott Kelly spent nearly a year orbiting the Earth at 17,500 miles per hour, his personal flow of time dilated. He aged 5 milliseconds slower than his twin brother, Mark, who remained on the surface. By the time Scott returned, he had effectively time-traveled into the future. His cells and his entire biological process were undeniably subject to the laws of relativity. Moving through space at high velocities acts as a one-way bridge into the future. The barrier to pushing a human years into the future is an engineering problem rather than a theoretical one. We routinely observe this time-stretching effect in subatomic particles pushed to near light speeds inside the CERN particle accelerator, the world's most powerful laboratory for high-energy physics. Future time travel is a proven, measurable mechanism operating all around us.